Okay, so again, I welcome all of you to this section of thermal engineering MEC551. Okay, so we have been discussing questions related to combustion. Okay, so this is our last chapter and last lecture for the semester. Okay, so I'll solve a couple of questions related to thermal engineering again, combustion, so that you have some experience on what to do during the final exams. Okay, so we'll take a look at this example. But before we look at this example, I would like us to, again, recapitulate the energy equation. Okay, energy equation related to combustion. In every combustion, okay, so we normally apply the first law. So application of first law of thermodynamics. Okay. So application of the first law of thermodynamics to combustion is like this, that, see, if we have a combustion chamber, okay, so imagine it to be a control volume system in which some amount of fuel is entering. Okay, so let's say we have air over here, and then we have fuel. And these are the product of combustion. From the first law of thermodynamics, we know that the total amount of energy entering a control volume system should be equal to the total amount of energy that is exiting the control system. So in every, for a control volume system, we have Q in, assuming Q in plus W in, which is the work input, okay, plus, then we have the fuel, so number of moles, the reactant, okay, and it's given by the enthalpy of formation of the reactant at standard state plus the enthalpy at a given state minus the enthalpy at standard state. Okay, so this is for the reactant. Okay, so this should be equal to Q out plus W out. Okay, this is just a recapitulation of what we did, plus, again, the enthalpy of the product. That's the enthalpy of the product. You have the number of moles of the product, okay, into bracket, followed by the specific enthalpy of formation of the product, plus the enthalpy of the product at a given state. I'll explain, we'll look at all this, okay, by solving a question related to it. Then minus the enthalpy at standard state. Okay, so now if you look at this energy balance for the control volume system in this combustion chamber, there is no Q in. In other words, there is no heat input. Okay, Q in equals to 0. There is no heat transfer to the combustion system. So therefore, you cancel Q out. So Q in is canceled out. And also there is no W in. There's no work input to the combustion system. But we have some reactant in the form of fuel and air that is entering the combustion system. So this particular equation, this part, is not equal to 0. But however, if you look on the product side, there is no W out. In other words, there's no work output. So in any combustion chamber, when you burn fuel, there is no work, there is no mechanical work. Okay, but we do have Q out. There will be, in addition to the product of the combustion, there will be some heat energy which is given out. So this Q out is never equal to 0. You understand me? So eventually, so we can say that Q out equals to the enthalpy of the reactant minus the enthalpy of the product. Okay, so we can rewrite Q out like this. Q dot, okay, should be equal to the summation of enthalpy. So we have the number of moles of the reactant into bracket HF, okay, at standard state plus H at the reference state minus HO, okay, at the standard state minus, again, I'll have enthalpy of the, number of moles of the product. Then I'll have HO, okay, for the formation plus H, that's at the given state, okay, minus HO, that's the enthalpy at the standard state. Okay, so this can also be written like this. Sorry, this can also be equal to HR, that's the enthalpy of the reactant, minus the enthalpy of the product. Okay, so that is Q out. That is our Q out. So we're going to apply this in solving question today. Okay, so our Q out can be given by this. Okay, so now quickly let us visit this question. Here we are told that E10 is a new type of fuel for internal combustion engine. Okay, E10 is a new type of fuel for internal combustion engine. It is blended, okay? It is the blend of 10% liquid of ethanol or liquid ethanol, whose chemical composition is this. And then 90% octane. Just like if you go to the Petronas station, okay, they have raw 95, they have raw 90 or whatever it is. So depending on the grade of the fuel you want to buy, okay, so raw 95, raw 90, raw 80 or whatever it is. Okay, so this, the fuel is blended with another type of, what do you call it, chemical or another type of fuel. Okay, so now, now the performance of this fuel is tested by burning it with 110% theoretical air. So you see over here, 110% theoretical air means that is 110 stoichiometric air. Now the fuel enters the combustion chamber at the rate of, okay, so 0.3 kilogram per second. During the combustion process, only 90% of the carbon in the fuel is converted into carbon dioxide. Okay, and then we have the remaining 10% forms CO. Now, both the fuel and air enter the combustion chamber at 298 Kelvin. If the product in the gaseous form leaves the combustion chamber at 480 Kelvin, determine the air-fuel ratio. Okay, so first thing we want to determine the air-fuel ratio, but be careful over here. We are told that the enthalpy of formation for the ethanol is given to be minus 277.690 kilojoules per kilomole. Okay, so we're going to make use of this particular value. Okay, so now let us draw the combustion chamber, okay, and then try to analyze it. We have the combustion chamber like this, okay, and then we have the fuel. So fuel is coming in. So now we have two different fuels. Okay, we have C2, that is the ethanol, H6, and then oxygen, H6, and then one atom of oxygen, plus C8, H what? H18, H18. And the percentage, you see, so the inlet, the percentage of the ethanol is 0.1, 10%. This is 10%. And this 10% equals to 0.1. And then this is 90%. And 90% is equivalent to 0.9 kilomole. Okay? Now, in addition to the fuel, we also have air. So the air enters the fuel as well. And here we are told we have 10%. Okay? 110 theoretical air. Let's see. 110, yes, let me see. Yes, 110% theoretical air, 110% theoretical air. And this should be equal to 10%. 10% what? Excess air. Or in other words, we can say it is equal to also 110% stoichiometric amount of air, like this. Okay, so now let's move to the product. So this is combustion chamber. In the product side, we have, we are told that the carbon is converted into, we have 10%, sorry, and the fuel enters the combustion chamber at 0.03 kilogram per second. During the combustion process, only 90% of carbon dioxide, of the carbon in the fuel is converted to CO. Okay, so it means the number of mole of the carbon dioxide in the product is CO. And the remaining is the remaining 10% forms CO. Okay, so we have CO2, 90%, and CO is 10%. So we need to account for it. Okay, so we have over here our carbon dioxide, CO2 equals to 90%, which equals to 0.9. And then similarly, we have CO is also equals to 10%, which is equal to 0.1. All right. So now, in addition to this product, there will be water formation at the product. There will be oxygen because of what? Because of excess air. So whenever there is excess air, there will be also oxygen at the product. And then eventually also there will be nitrogen at the product. Now let us look. The temperature at the beginning or the inlet to the combustion is the operating temperature, T in, equals to 298 Kelvin. And then the temperature at the exit. So T out equals to 4. So how much is it? 480 Kelvin. So you see that the temperature above the inlet and exit, they are completely different. Okay, so we need to take note of this. Very, very, very important. So now, the question wants us to determine the air-fuel ratio. So the first thing to do before you determine the air-fuel ratio is to write down the combustion equation. Okay, and again, like I always tell you, we need to first write down the stoichiometric equation. Okay, first thing first. So first, write down a balanced stoichiometric equation. Okay, so how do you write it? So stoichiometric equation means this implies 100% theoretical all right. So now first we start with the fuel. In the fuel we have C2H what? H6. Then we have oxygen. What is the mole of the amount of C2H6? Okay, 0, or the ethanol that enters the combustion chamber is 0. That is 10%. So that gives a 0.1 kilomole. Plus, again, the fuel also, that is 0.9, 90%, 0.9 kilomole of C8H18, like this. Then we have the air. So we don't know how much air enters, so we represent it by the theoretical amount of air. So in this air, we have 1 kilomole of oxygen plus 3.76 kilomoles of what? Nitrogen. Okay, for every 1 kilomole of every 1 kilomole of oxygen, there will be 3.76 kilomole of nitrogen that is present in air. Okay, so it means if you take some amount of air, for any amount of air that you take, any sample of air, there will be, for every 1 kilomole of oxygen, there will be 3.76 times number of moles of nitrogen present. Okay, just like maybe you are in a classroom. For every 1 lady in the classroom, there will be 3 boys. Okay, so that's the implication. Okay, for every 1 lady in the classroom, then there will be 3 boys, like this. So that's the ratio or the total amount of students that is present in the class. Okay, so the total amount of students present in the class will be 4. You understand me? Okay, but for every 1 lady, there are 3 boys in this way. So now, let us write the product side. Okay, so at the product side, so I've told you again, for a theoretical air, or let's say stoichiometric equation, we always assume that this is a complete combustion. So if it's a complete combustion, it means at the product you have carbon dioxide plus what? Plus water. And then plus what? Plus nitrogen. So this is the condition under which complete combustion takes place. So if you bring carbon dioxide, if you bring carbon monoxide, that is CO, oxygen in this equation, then the whole thing will collapse. Then the whole definition for stoichiometric equation is going to collapse. You understand? So for the necessary condition for a complete combustion or stoichiometric equation is that you should have carbon dioxide present, you should have water at the product, and nitrogen. So, but we don't know what is the number of moles of carbon dioxide, water, and nitrogen that is present. So we represent by X, Y, and then Z. Okay, so now we're going to balance this equation. So carefully, we start first with carbon. Okay, so let us balance carbon. So for carbon, we have, let's say, 2, okay, so 0.7, 0.1 times 2 over here. So for the ethanol, we have 0.1 times 2 atoms of carbon plus, again, 0.9 times what? Times 8. Okay, so this should be equal to And this gives us, we have X of carbon dioxide. So we have X moles of carbon dioxide. So we have X of carbon dioxide. So it means X equals to 0.1 times 2 plus 0.9 times 8. Okay, so eventually we will have, let me see over here, 0.1. So that gives us 0.2 times 0.9 times 0. Sorry, we have so let me see. That'll be 1.8. So that gives us 7.5. Okay, so X equals to 7.5. X equals to 7.5. So X equals to 7.5. Now, if we have to balance the hydrogen also, so in the same way, so for hydrogen, we will have a situation like this. 6 times 0.1, okay, so 6 or 0.1, 0.1 times 6, okay, plus 0.9 times 18. Okay, this should give us 2y, 2y, right? So if you solve this carefully, y gives you 8.4. All right, so now let us consider the oxygen. Oxygen now gives me, I have, be careful over here, we have 0.1, we have oxygen over here. Okay, so this gives me, but here we have only one atom of oxygen. Okay, so that gives us 1 times 0.1. Okay, so that gives us 0.1 times 1 plus, again, we will have 2 ATH moles of oxygen. Okay, this should give me, here we have X, 2X at the product side plus Y. Okay, so now carefully, if you balance the oxygen, this gives me, we know the value for X. X is equals to 7.5 and Y equals to 8.4. Okay, so we will have, let me see, 2 times X, 7.5 plus 8.4. So carefully, the theoretical amount of air equals to 11.65. Okay, so now we're going to write down the complete equation, okay, for the 100% theoretical air. Then we're going to look at 10% excess air. Okay, so then that gives us the final equation, gives me 0.1 C2 H6 oxygen plus 0.9 So we have 0.9 times, this gives me C8. So C8, then we have H18 plus, now we know the theoretical amount of air, which is 11.65. 11.65. Then we have oxygen plus 3.76 of nitrogen. Okay, so eventually we'll have at the product site, let's see, X we know to be 7.5 carbon dioxide. Okay, so plus Y 8.4 of water. Then finally, oh, we have not calculated that of Z. I'm very sorry. So we need to calculate the one for nitrogen. Okay, so nitrogen has not been balanced. Sorry. So let's see. Let us write down there. So for nitrogen, we have, so that is N2. This gives me, we have this ATH, we have already calculated 11.6. So we have 11.65 times 3.76 times 2. This gives me 2Z. All right. So 2 cancel 2 over here. So eventually Z will be equal to, let's see over here what is Z. So 11.65 times 3.76. So 43.8. Okay, that is for nitrogen. Okay, let me cross check again. I have over here nitrogen, so 2 times 3.76 times this. All right, so then we have Z equals to 11. So 11.65. Okay, so times 3.76. Okay, so now it's compared. So we have 43.804. Okay, so approximately 43.80. Okay, so now we'll write down the whole equation. So it's very long equation. So we have C 0.1 C2H6 oxygen plus 0.9 C8H18. Okay, so plus air, the stoichiometric amount of air which we got was 11.65. Right? So then this gives me oxygen plus 3.76 number of moles of nitrogen. Then at the product side, I'll have, let's say, how much was carbon dioxide? So carbon dioxide is X 7.5. So that gives us 7.5. Okay, so 7.5 carbon dioxide plus carbon dioxide, and then we have water also, so 8.4, so 8.4 amount of water. So then, yes, then we have 43.8, 43.804 of nitrogen. All right. So this is the equation for the complete combustion situation. So now, what we need to do is to write down, okay, so one, write down equation, write down balance equation, okay, for 110% theoretical air. Theoretical air. So now what we will do, just a repetition of all that we have written before. So we have 0.1 C2 H6, and then we have oxygen plus 0.9 C8 H18 plus now 1110. Be careful over here. When we say 110, okay, theoretical air or stoichiometric air, percent theoretical air, theoretical air, it is equal to 1.10. Okay, so 1.10. So we're going to add these two, multiply it by the percentage of the molecular mass of the air over here. So let me use a different color. So we will multiply 1.1 by this. So let me use a different color. So 1.1 is going to multiply this. Okay, so this equation. Then we will have 1.1 times 11.65. So 1.1 times 11.65 of oxygen plus, again we have again 3.76 number of moles of nitrogen. So eventually this gives me. So at the product side now, be careful over here. At the product side, so we are told 90%, okay, of the carbon dioxide is formed. All that, and the 90%, let's see again, let's visit the question. So we are told 90% of the carbon in the fuel is converted into carbon dioxide. So this is the actual combustion now. In the actual combustion, 90%. So we are going to put 0.9 times, and the number of moles for carbon dioxide we know already. So in the original equation, it is 7.5. You understand? So we'll multiply 0.9 by this 7.5. Okay, so we will have times 7.5 times 7.5. And then we will have of carbon dioxide. carbon dioxide. Then the water remains the same. So it's not affected in any way. So we have 8.4 moles of kilomoles of water. Now we have again carbon monoxide. Okay, be careful over here. We have carbon monoxide and oxygen that will be present, and we are told that we have 0.1% of carbon monoxide is given at the product side. Okay, so we will have 0.1 of carbon monoxide plus 0.1. Then we have to know that the amount of carbon dioxide that is given over here in the original case will be the same. In other words, or we can represent it, let's say, if we don't know the number of moles of carbon dioxide that is present, we can represent it by X. So let's say X of carbon and the carbon monoxide. Okay, so then plus X moles of oxygen or Y moles of oxygen in the product. All right, then plus again the number of moles for nitrogen. So nitrogen now gives us we have in the nitrogen case we have 11.65 times 3.76, okay, times 1.1, or in other words, this, the whole of this. Okay, so this gives me, let me do the multiplication, 1.1 times 11.65, then times 3.76. So 48.1. In other words, or approximately 48. Okay, so this gives me, I will have 48. So what I did over here is 1.1 times 11.65 times 3.76. Okay, number of moles of nitrogen. Now, we need to find the actual moles of carbon monoxide that came out over here. And then we are representing, maybe I should represent this by use a different notation here. Okay, so let's say, so let's represent this by P. So P amount of carbon monoxide is given. But we know its percentage is 0.1. That's 10%. Okay, but for oxygen, we don't know. So first, let us balance the carbon monoxide. Okay, so we'll balance the carbon monoxide by balancing only carbon. Okay, so considering carbon, we will have, again, we will come to the initial state, 0.1 times 2 plus 0.9 times 8. That's for the fuel. And then this should give me, at the product side, I have 0.9 times 7.6, okay, for carbon, okay? So I'm looking at carbon, plus, let's see, plus OP, so 0.1 P, 0.1 P. So now let's look what is the value for P now. If I sum this, this gives me 0.2 plus, let me see, 8 times 0.9. So this gives me, okay, Now, and let me see, plus 0.2. So that gives me 7.4. So I have 7.4 right here. 7.4, and this should be equal to 0.9. 0.9 times 7.6. Okay, so now minus 7.4. 7.4. Okay, times, so that is 0.56. 0.56 divided by 1. 0.56 divided by 0.1. So I get 5.6, okay, of carbon monoxide. 5.6 of carbon monoxide. In other words, P equals to, if I multiply this, okay, so I'll get P equals to 5.6. Now let us calculate that for oxygen. So that of oxygen gives me, let me cross-check this answer again. So here I have 0.1 times 2, is this correct? So 0.9 times 8. Okay, so then I have again carbon again in this equation. So 7.5. Oh, yes, I made a mistake here. So 7.5 times 0.9, 7.5. So there is a mistake here. 7.5 times 0.9. Okay, so then plus 0.1 times P. So let me do the calculation again. So we have 0.9 times 7.5. Okay, so minus 7.4. Okay, 0.65. So that gives me 6.5. Okay, so it's supposed to be 6.5. So P equals to 6.5. Now let's find the value for X. So now X gives me, oh, so to find a value for Y, that is oxygen, we will have balancing of oxygen gives me, so 0.1 again. So I have 1 atom of oxygen at the internal site. Then again, I have plus 11 or 1.1 times 11.65. All right. So plus and times 2 moles of oxygen. So then this gives me, this should be equal to 0.9 times 7.5, okay, times 2, okay, plus, again, I have 8.4, okay, so 1 atom of water, oxygen in the water. Then I have 0.1, okay, times P. P is 6.5 plus Y, 2Y. Okay, so now let's find the value of y. If you do this carefully, x is going to give us, for oxygen, x is going to give me 1.17. 1.17. Okay, so that is it for the equation or balancing of the of this particular equation. So now we'll rewrite the whole equation again. Okay. So rewriting the whole equation, we will have 0.1 C2H6 oxygen plus 0.9 C8H18 plus. So now if I multiply all these things, that gives 12.82. And then oxygen, so oxygen plus 3.76 nitrogen. Okay, so then this gives me, for carbon dioxide, I get, let me see, 6.75. Okay, 6.75. 6.75 of carbon dioxide. Carbon dioxide. Then carbon monoxide, water, 8.4 moles of water. Then I have carbon monoxide, that gives 6.5. So I have 6.5 of carbon monoxide plus oxygen. Now oxygen gives me 1.17. So 1.17 of oxygen, and nitrogen gives me 48 kilomoles of nitrogen. Okay, so this is the actual equation, actual combustion equation. Okay, so so now let us determine the F-well ratio. Okay, so F-well ratio gives me the F-well ratio for the actual combustion equals to mass of air divided by mass of fuel, mass of the fuel. So this gives me, we have in the oxygen side, the air side, we have 12.82 kilomoles. Okay, kilomoles of the air times the molecular mass. So molecular mass of the air, okay, so times, we will have times 29, 4.76. So I should rewrite this equation. So it should be like this. It should be like this. And let me see over here. And that gives me 82. Okay, so times 4.76. Okay, kilomoles. 4.76 kilomoles times 29 kilogram per kilomole. Okay, then all divided by. So now, if you look at the fuel side, we have 0.1 kilomole of the ethanol. Okay, so 0.1. So then times the molecular mass of the ethanol. So molecular mass, we have 2 carbon, okay, and then 6 hydrogen, and then 1 oxygen. So if you combine all this, you get 46, okay, plus, and again, for the fuel, you have 0.9, okay, so all the molecular mass for the fuel is this, okay, so all of this gives us the air-fuel ratio gives me 16.4 kilogram of air per kilogram of fuel. Okay, so that's the important thing we have already determined. Now we have to determine the next question is to find the rate of heat transfer from the combustion chamber. Okay, so rate of heat transfer from the combustion chamber, we need to determine H. So for the B part, or II part, rate of heat transfer, this is given by enthalpy of combustion, okay, is the same as let's say, HR minus enthalpy of reactant. Okay, but take note that the heat of combustion is always given by enthalpy of combustion, which is equal to the enthalpy of combustion divided by molecular mass of the fuel. This is very important, mass of the fuel. Okay, so the difference between H bar and H is that, see, this is a specific quantity, okay, which is the same related to the QC, that's the heat of combustion. Okay, so now we're going to determine HR. Okay, so find enthalpy of reactant first. Okay, HR. Yes, HR first we are going to determine. So now, what is the formula for this HR? It is given by, we have the sum of the number of moles of the reactant times H enthalpy of formation at standard state plus the enthalpy at the given state plus, minus, I'm very sorry. So it should be minus enthalpy of formation at the standard state. Minus the enthalpy at the standard state. So this. Okay, so if we look in the reactant side, first let us take C2H6 oxygen. Okay, so this implies that we have the number of moles of this fuel is 0.1. Be careful, please. Okay, then the enthalpy of formation for this fuel is given in the question. Look, the enthalpy of formation Okay, it's given in the question. Here is it. So the enthalpy of formation for ethanol. Okay, so ethanol is given. Okay, but octane is not given. So now this gives me minus 277, okay, comma 690 plus. Now this is where the students find problem. Be careful over here. Now enthalpy of this fuel, let's say the enthalpy of the ethanol at 25 degrees Celsius and its enthalpy at the standard state are the same. So it will be equal to 0. See? So let me make it clear to you. The enthalpy, what I'm saying that enthalpy, so unfortunately, let me see if I have the property tables where I can easily illustrate this thing. So let me open my property table. See, just 1 minute. So I hope you have your property tables with you. Okay, so it's very important for this discussion. So I'm trying to search for the property table. Where we can easily read these things. So the enthalpies, what is of oxygen? Yes, so let me upload this. Yes, so this is the table I'm talking about. You see that in this table we have the enthalpy of formation. Enthalpy of formation for carbon monoxide, carbon equals to 0. Enthalpy of formation of hydrogen is 0. Because all these elements, they exist in their natural state. But the enthalpy for formation of carbon monoxide, carbon dioxide, okay, so different fuels, methane, ethane, ethylene, so all these they do not exist in their natural state. So their enthalpy of formation can be, is given. Okay, so now let's see in the question that we were discussing. So now, so like I was telling you in this particular question, the enthalpy of formation for the ethanol and this enthalpy at the standard state, that is at 25 degrees Celsius, okay, will be equal to 0. Now, if you have your property table with you, maybe you can open to, let me see, page 41. Okay, so page 41. Unfortunately, I cannot put all the 2 slides on the same presentation, so we have to be a bit cautious of this. Okay, so it's very difficult to combine 2 slides. Okay, so here I'm going to have, we will have 0. Again, here I'm going to have 0. So enthalpy, so this will give me 0, and then plus this gives me minus 277,690 kilojoules per kilomole. Okay, so let's see. Kilojoules per kilomole. Kilojoules per kilomole. Now, next, if you want to determine the enthalpy, the enthalpy of the reaction for, let's say, next for water. For water, we have, this gives me so 1 minute. Okay, so yes, so for water, we will have a situation like this. So this gives me 8.4 kilomoles times enthalpy of formation for water. If you look into the property table, the enthalpy of formation of water at standard state, okay, is this we have to look from the property table. It is given over there. Okay, so that gives us minus 241 water vapor, 241. So maybe I should show you. Let me show you that one. So it's a bit challenging over here. So here we have the enthalpy of formation for water. It's given, where is it for water? Yes, water vapor. Okay, so liquid water is we don't use the liquid water. Okay, because during the combustion, any amount of water that is present will be in the vapor state. It's not going to be in the liquid. Otherwise, there will be no combustion taking place. Okay, so the enthalpy of formation for water is this. Okay, and then if you go again to the property table at 25 degrees Celsius, so at 25 degrees Celsius, let's see, for water, let's see, properties of water at 25 at 25 degrees Celsius. Yes, so 25 degrees Celsius or 298 degrees Celsius, the enthalpy, let me see over here. Yes, that enthalpy is given by the enthalpy of 298. So we are told the combustion, please pay attention over here. The combustion takes place at 298 Kelvin. And the enthalpy of the water, enthalpy of water at the given state, or let's say at temperature equals to 298, okay, 298 equals to, let me use a different. So I'm trying to explain something to you here, but pay attention. So the enthalpy of water at temperature 298 Kelvin equals to 904 kilojoules per kilomole. But again, if you are asked to, you see, the equation that we were discussing, that equation is like this. So we have N number of moles of the reactant, okay, times enthalpy of formation at standard state, plus the enthalpy at the given state, okay, minus the enthalpy of formation, minus the enthalpy at standard state. So enthalpy of water and standard state, that is what I've explained over here. Enthalpy of formation of waters at standard state is given here. You see, enthalpy of formation gives functions, and absolute entropy at standard state means 25 degrees Celsius, which is the same as 298 Kelvin and 1 atmospheric pressure. Okay, so the enthalpy of water vapor or formation of water vapor is this. This HF bar is this one. This is different from the enthalpy. Okay, you see the enthalpy of the water at a given state. Given state means, so we have 25 degrees Celsius, 298 Kelvin. That is for this one. Okay, that's this enthalpy. And similarly, if you want to find the enthalpy at standard state, it's the same thing. Here, at a given state means, look, we have in the combustion chamber. In the combustion chamber, we have fuel going inside, fuel. And we have air also going inside. Okay. And the fuel is such that it is mixed, it is not a dry fuel. So there is some moisture in the fuel, which comes out as water vapor. And at this temperature of at 25 degrees Celsius or 298 Kelvin, that is the inlet condition of the fuel or the water. Okay, so whenever we say H bar, it means we are referring to the enthalpy at the given temperature. At a given temperature, and that temperature is equal to 298 Kelvin. And similarly, the enthalpy at standard state. What is standard state? Standard state is the same. It's the same as at temperature of 298 Kelvin. So this enthalpy, which we have already noted, is given by this. So it means both HO bar is the same as H at a given state. You understand me? So because you are going to get 9, that gives us 9904 minus 9904, which is equal to 0. You understand? So, and that's how we are able to solve this equation like that. Okay, so like this. So now we will have, let me upload the slide again for you to understand. We will stop very soon. So we have, so like I've told you, we have the enthalpy of formation for the water is given already, which is equal to 241 minus 241, okay, 820, okay, plus, oh, sorry, I made a mistake here, sorry. So this gives me, so it, a bit challenging, so try to solve more questions on your own, and if you have any problem, you contact me. So minus 249, 595,950 plus 0, let me see, and this gives me, yes, the enthalpy of water at 25 degrees Celsius. How much is this? This gives me, let me see. Yes, so 29 at 298 Kelvin, 99, I'll get 9, okay, 04 minus again 9904. So that gives us 0. Okay, and that gives us 0. So then this, if you calculate, this gives me minus equals to minus 249, okay, comma 950. Then if you look for oxygen, so for the oxygen, let's consider oxygen. So for oxygen, this gives, we have 12.82 kilomole of oxygen in the product. So you see, this is the kilomole of oxygen. So this gives me, 12.84 kilomoles of oxygen. Now, tell me, the enthalpy of formation of oxygen is 0 because oxygen exists in its natural state. Plus, you see, the enthalpy of oxygen at the given state means 298 Kelvin. So that gives me 8682 minus at its standard state. Again, it is the same, 8682. Okay, so then it means the whole thing is 0. Okay, so the whole thing becomes equals to 0. So we will have 0. We have 8682 minus 8682. So this also equals to 0. Then for nitrogen, nitrogen gives us, we have 48 moles of nitrogen. So nitrogen also is 0 plus enthalpy of formation of nitrogen. Sorry, enthalpy at given state. This is 8669 minus 8669. So again, this gives us 0. So therefore, we will have H bar R for the reactant is minus 527,460 kilojoules per kilomole. Okay, So now, quickly, before today I've taken much of your time. So now let's go to the product side. So consider the product. At the product side also, we have H bar product gives me sum of the product. So then I'll have H enthalpy of formation at standard state plus the enthalpy at the given state minus HO. Okay, so now we consider carbon dioxide. Carbon dioxide first, that gives me 6.75. Okay, now enthalpy of formation of carbon dioxide is minus 393, then 520, plus now the enthalpy at the given state. So be careful over here. So now you see that at the product site, what is the temperature? The temperature at the product site is not at standard state. So the temperature at the product site is different. Be careful. This is the product at the reactant. So the temperature at the reactant is this. This is at standard state. But the temperature at the product site is different. This is not a standard state. This is at a given state. Given state. You understand? Which is completely different from the standard state. Okay, so we are going to look for the enthalpy for the enthalpy of formation for carbon dioxide is this. There's no way. This is also in the property table. And the enthalpy at the given state means H bar, okay, for carbon dioxide at the given state. This equals to, if you read carefully from the property table, this gives me 16,791. Whereas the enthalpy of carbon dioxide at standard state is also different. So this is the enthalpy at standard state. This is the enthalpy at the given state. So you will say this is at, let me see. So let's see right here. So this is carbon dioxide. So the enthalpy of carbon dioxide at the given state. So at 4, let me see, what is the temperature? Yes, 480 Kelvin. So 480 Kelvin. So that enthalpy is given by, we'll have 16, okay, comma 791. Okay, and then the enthalpy at standard state. Okay, this is for carbon dioxide. So at standard state means at 298 Kelvin. So this gives me 9, okay, comma 364. Okay, so this is for carbon dioxide. Okay, so carbon dioxide. If you put into this equation, it gives me 16, okay, comma 791 minus 9, 364. Okay, so if you solve this carefully, this gives us minus 38 minus 38. So minus 38 6, okay, 093. Okay, so now for water also, if you consider the water, we will have the enthalpy. So its mole is 8.4. And then we have the enthalpy of formation of water is minus 241. Okay, then we have 8.20 plus the enthalpy at the given state 16,126 minus 9,904. Okay, so this gives me minus 235. Okay, so 598. Okay, so now next we have carbon monoxide also at the product. So carbon monoxide. So we have 0, C0. So this gives me, and let's see over here, 6.5 minus, so we have 110,530 plus 14,005 minus 8669. So eventually this also gives me 105, okay, 105, 194. Okay, so minus. So it's minus. So I'll take about 3-5 minutes of your time, right? So that is it. So now if you do the same thing for oxygen, okay, so we have oxygen in the product, right? So that gives me 1.17 kilomoles of oxygen. Enthalpy of formation of oxygen is 0 plus the enthalpy at the given state, 14,151. 14,151 minus 8682. So this gives me, if you calculate carefully, this is positive, not minus. So 5,469. Okay, lastly, that for nitrogen. So I'll have 48 kilomoles of nitrogen. So I have 0 plus 13,988 minus 8669. Okay, so this gives us 5,319. So eventually, HP gives me minus 716,097. Okay, so now to find the enthalpy for the combustion, this gives us H. We have already said this gives us HR minus HP. So this gives me minus 527,466 minus, again, minus 716,097. Okay, so eventually I'll have positive 188,637 kilojoules per kilomole. Okay, so almost done. So eventually we will have the enthalpy of combustion. So this equals to HC equals to H bar divided by mass flow rate of the fuel, or mass of the fuel. So this gives me 188,637 kilojoules per kilomole divided by the molecular mass of the fuel, 0.1 for ethanol, 46, and then for octane, 0.9 times 114. Okay, kilojoules, okay, per kilogram, per kilomole. Okay, so per kilomole. So now this gives me, this is kilogram. So it should be kilogram per kilomole. Kilogram per kilomole. So kilomole will cancel kilomole out. So the result now gives me 10,967.3 kilojoules per kilogram. All right. So now to find the heat of combustion, so this is Q dot equals to Q C times mass flow rate of the fuel. So mass flow rate of the fuel is given. So now this gives me 10. Okay, so this is my QC. So 10,967.3 kilojoules per kilogram times mass flow rate. So 0.03 kilogram per second. So now this gives me 329 kilowatts. All right. So now to determine the air fuel ratio, from air fuel ratio AF, we can define that this equals to mass flow rate of the air divided by mass flow rate of the fuel, which is equals to 60.4. So from here we can find mass flow rate of the air equals to 16.4 times 0.03. So eventually we'll have 0.492 kilogram per second. Okay, so this brings us to the end of this class. Okay, and now, the last one. So the last part, it says incomplete. So what are the conditions for incomplete combustion? Okay, so this you can get from your lecture notes. The presence of carbon monoxide in the product gas is direct indicator of incomplete combustion. Define incomplete combustion and discuss two possible causes leading to incomplete combustion. So incomplete combustion is it's a situation where we have, if you have in the product, let's say the product contains unburned fuel. For incomplete combustion is a situation, so incomplete equals to, okay, so combustion product implies combustion product contains any unburned fuel. Contains any unburned fuel. Okay. okay, such as CO, hydrogen, and then OH. Okay, so what are the causes of incomplete combustion? Causes. Causes means one, insufficient what? Oxygen. And then number two, also insufficient mixing. Okay, so that brings us to the end of this question. If you have any question, please, can you let me know, please? And then we discuss. So is there any question from anybody? Otherwise, then I think we will end our class over here. Okay, so if anybody has any question, then maybe you can WhatsApp me. If I have some questions and solution, I will send to you as well.